Hi, this is David. We're going to be talking about MLE parameter estimation method. We're going to cover what it is and how you go about doing it. So, what is the MLE parameter estimation method? The MLE most likely estimator method is one way to determine the parameters that describe a distribution associated with a data set. It works by forming a scalar value, a likelihood value, which is somewhat similar to a p-value that has been discussed in class, for a given data set and a set of distribution parameters. The parameters we're talking about are like the mu and sigma for a normal distribution. Then it seeks values for those parameters that maximize that likelihood. So let's take a look at some examples. Here's a data set that is a relationship between x and y. Right now it's just some discrete data points. But what we would like to do is form a mathematical relationship between x and y. And the easiest way to do that, of course, is to just let Excel do it for us. We're going to have Excel add a trend line. We're going to let it be linear. And there it is. So what we've done here is drawn a line through the data that is, well, seems like a pretty good fit. You can imagine if the line was up here somewhere, that would not be a good fit. Let's have Excel show us what that line is. And here you can see it. There's the slope, 0.9841, and there's the intercept, 0.1707. Now the question is, how did Excel come up with these values, the slope and intercept? Now the way it came up with these values was it used the least squares method. So for every data point, it looked at the data point, it evaluated the distance to the to the line in terms of y, squared that distance, and then added that to every other squared distance. Once it did that, it looked then for values of the slope and intercept that minimized that sum of squares. Now that's fine for data where we have a relationship like this, but what if we have just random data? And I have a set of random data here. It's from a random variable. And, well, let's see if we can analyze it, see what we can see. Let's try inserting a graph. Okay, that's, I guess, helpful. I'm not sure. I don't honestly see what kind of pattern this is other than it's random and it seems to be centered around probably 100. But we could have seen that by just doing this, and Excel shows me that the average was 97.4. So that's not terribly helpful. Let's delete that. Let's try something else. Let's try inserting a pivot table. I'm going to put it here. I'm going to group the data and get the respective counts that are in each one of these buckets. Now you can see something going on here. Let's insert a graph. Okay, well, we're seeing something. Maybe this has the shape of kind of a normal distribution. It's kind of hard to tell. Maybe it would be helpful if we regrouped it with a slightly different setting. Let's put that to 5 instead. Okay, well, kind of helpful. Looks kind of flat here. Doesn't exactly have what we might think of as a normal distribution, but even then, I'm not real sure what this is telling me. Maybe let's try something different. Let's just go ahead and get rid of this pivot table for now. Let's try something completely different here. Let's put in, instead of trying to plot it as a histogram or a PDF, let's try plotting a CDF, the cumulative distribution function. And the way we're going to do this is we're going to set the increment for a fixed increment or percentage associated with each data point. So I'm going to say this is equal to 1 over the count of the data. Here I'm going to set that equal to that, and this equal to this plus the increment, and make sure we anchor that. Now we can just drag this down. And if we will plot this now with a scatter graph, we get a tornado. And that's because we didn't sort the data. So let's sort the data over here. Do not expand the selection. Continue with the current. We don't want to sort the CDF column. That would mess it up. So let's just sort this. Now we see something that's starting to look like a CDF. Starts at 0, ends at 1. That's what all cumulative distribution functions do. And let me see if I can get this looking a little better. At about 70. And now what I want to do is actually put the parameters on there that we kind of expect. We think this might be normal, so let's write that. And over here, let's figure out what the normal parameters are. They're the mean, or the average of the data set, and the standard deviation. We use the sample. And let's see what that does for us. We'll pick up the data point. Oops. Pick up the mean, the standard deviation, and we'll tell it that we want the cumulative, or true. Now let's go back and anchor our data, our parameters, so we can drag this down. Now let's just double click this down. Let's go in here and add in the normal column that we just got. Wow. Okay, so this CDF represents the actual data, and this normal represents the curve we just now generated. Okay, very good. Now, but what happens if we have some data that is not necessarily normal and we don't really know what we're doing? And here I have a data set, and once again, looks like my 2-year-old got here with the crayons before I did. So let's, and again, this is because I don't have the data set sorted, so let's sort it. Now, in this case, I've tried to use a normal, and I've done the same thing. I've set that to the average and this to the standard deviation, but you can see that is not a good match. And I think the real problem here is that normal is not a good fit for this data. I'm going to try a Weibull distribution. And in this case, I know some things about the Weibull. I know that this should really be called the shape. Here they call it alpha and beta, but it's really shape and scale. So the shape controls the shape of the curve, and the scale controls where it's situated on the curve. So the scale we should set to about where the line here, the data line, crosses the 63% mark. And that looks to be about 75. We'll put that to 75. And then the shape is usually somewhere between 0.25 and 4. We'll just start off with 1 and just guess at it. Oh, well, that's better. Let's try 2. Okay. Let's try something else. 1.5. Seems like we're getting there. Looks like our scale needs to move a little to the left. Let's set that to 70. You can see we're starting to get there. The question is, in fact, I guess really this should be 1.6 maybe, and 68. I had tried those values earlier and gotten fairly good results. The question is, instead of guessing, is there a way, a systematic way, to come up with these numbers um, by some process? And the answer is yes. We can use least squared, like we did with the relationship data earlier, or we can use this MLE most likely estimator approach. So let me bring up now the spreadsheet that I'll be turning in for my semester project. And here is here's my raw data. Here's my failure data, or just data from the random variable. I call it failures because I'm using this in the context of machinery where we have failures. One of the really nice things about the MLE approach is that we are not limited to just failures. We can also put in suspended data points. Suspended data points are data points where we don't actually experience a failure, but we maybe have to shut off the test early. This would be a right suspension. I'm not going to get into all the details of what all these suspensions are. So in the case where we have no suspensions, and I have this set has 0 suspensions in it, we can use the least squared approach and see how that works out for us. So here I have a least squared fit. Let me go in here and change these values so we can see how this works. I'm just guessing maybe, and I've drawn a graph here to help me guess some good values. But I don't want to guess. I want to use an actual systematic process. So here's what I've done is I've developed a derivative, which this is the least squared approach. We've taken the derivative with respect to the different parameters. There's 2 parameters in this case. And we're going to try now to use the goal seek function in Excel. Let me see if I can show you that. It's under what if analysis, goal seek. We're going to goal seek this value, the derivative, to 0 based on these 2. And I've written a little 20-line macro to do that for us. So let's just watch what happens when I push the button. And you can see now that the least squared line overlays the actual data line almost perfectly, and it has in fact reproduced almost identically the original values that I actually used to generate the data. So these should be the population values, and you can see that we got really, really close. This is the least squared. There also is the most likely estimator approach. Again, we can mess these up. 500. And this is a real similar thing, except that now instead of minimizing the parameters around a least squared, we're minimizing that scalar value called the likelihood. And once again, we hit the little macro button here and let it do its thing. And once again, it hones in very closely on the original values from the population. The way this works is we have the distribution in here, and in each case I have a little minus sign. So this is my shape, this is my scale, or alpha and beta as they call it, and in each case I'm taking a little minus terms. What those are is my epsilon terms. So I look back over here, that's my purple one, and there's my epsilon value here. So in each case here, this is going to be the epsilon for the shape, and this is going to be the epsilon for the scale. If I switch this to 2, then this epsilon shows up as a finite value, and this one goes to 0. So I'll put it back to 1. And this one went back to 0, and this showed up as a finite. So in this column, each of my parameters has a little negative sign associated with an epsilon term. In this column, they have a plus sign. Other than that, they're identical. So negative positive. What I do then here is this formula sums up all of my plus terms minus all of my minus terms divided by my epsilon terms, that's these here, and multiplied by 1,000 just so that it won't quit early. It'll go ahead and goal seek for quite a while. And that is really all there is to this. We then let the computer look for the values, these parameter values, that force this term to 0. Like I said, we can do this with suspensions. Let me show you what this looks like with some data suspensions in it. Here's the same data, but now with 40 suspensions. So I've taken the last 40 data points and I've moved them over to simulate an inspection. For some reason, we say we don't want this thing going to failure. So at 950 hours, we force the components off into maintenance. And you can see these were the actual random values that came from the distribution, 955, 962, 970. But I've replaced those with just straight 950s, as I said, to simulate an inspection and repair. Now we go ahead here and we have a slightly different equation. We still pick up the failure terms, but we also have terms for the suspended values. And once again, we can run this and just watch what happens. And once again, it hones in very closely on the original population values that I used to generate these. Well, that's all I really have time for. I'm probably long on time now. I hope you enjoyed it. Thank you.